Welcome back to Regional Conference on Solid State Science and Technology, RCSSST 2022. So ladies and gentlemen, we shall now continue with the first plenary talk sessions. So my name is Technologist Dr. Teo Pauter, a senior lecturer of Materials Technology Programs, Faculty of Bioengineering and Technology, University Malaysia Kelantan. So I will be the moderator for the plenary talk sessions. First and foremost, let me introduce the first plenary speaker of RCSSST 2022, Professor Dr. Nafisah Muhammad Isa, alias OSMAN from University Teknologi Mara, UITM. Professor Nafisah is a professor at the Department of Physics, Faculty of Applied Sciences, University Teknologi Mara, UITM. She completed her PhD at University Kebangsaan Malaysia in year 2010 and her master science as well as undergraduate studies at the same university in 2002 and 1990 respectively. At the national level, she has been a secretary of the Malaysian Solid State Science, Technology and Society, MAS, since 2016, and a member of Malaysia's Associations of Hydrogen Energy since 2017. Her research interest lies in the areas of advanced materials, solid states ionic, materials chemistry, and generally the materials for proton ceramic fuel cell. In a recent study, she focused on better techniques for synthesizing ceramics compound at relatively low temperature and fabricating anode-supported single cells with various pure and composite materials of cathode and anode. She actively collaborates with researchers from other university and research institutes in several other disciplines of science and technology, particularly in materials for ionic conductor. Professor Nafisah leads the Physics and Chemistry Materials Research Group and Proton Conducting Fuel Cell Research Group in UITM. So ladies and gentlemen, without further ado, I would like to invite Professor Dr. Nafisah Muhammad Isa, alias Osman, to deliver the plenary talk entitled Electrical Performance of Proton Ceramic Fuel Cells at Intermediate Temperature. An overview. So please welcome Professor Nafisah. The floor is yours.
Assalamualaikum. I have 40 minutes, right? My session? Okay. Assalamualaikum and good morning. Today I'd like to say thank you very much to the organizer for inviting me to give a talk on our research group to share a part of our study or research on the solid oxide fuel cells. Okay. My name is Nafisah Osman. I'm from, we have UITM have a bigger campus, many campus. So I'm from UITM Perlis. Okay. In terms of fuel cells, okay, there are several types of fuel cells. We have phosphoric acid fuel cells, we have molten carbonate fuel cells, we have solid oxide fuel cells, direct methanol fuel cell, alkali fuel cell, and proton exchange or PEM fuel cells. But today I'm focusing more on the solid oxide fuel cells. If we go to the deep on the solid oxide fuel cells, we have two types of solid oxide fuel cells, which is can be differentiated by the electrolyte materials. If we use oxygen ion conducting material, we see it as oxygen ion solid oxide fuel cells. If we use proton as electrolyte material, so that solid oxide fuel cell is known as proton solid oxide fuel cell. This proton solid oxide fuel cell is also known as a proton ceramic fuel cells. Okay, so in terms of research for the solid oxide fuel cell, we can go on the materials to study more on the material of the solid oxide fuel cells, or we can go for the and we can go for the single cell. Then we can move to the stacked cells in terms of the planar or tubular solid oxide fuel cells. But in our research, we're focusing more on the single cell of the solid oxide fuel cell, which is we aims to go for the stacked cell in the future. Okay, in the proton ceramic fuel cell, we have three components, three main components, which is electrolyte and electrode part, which is for the electrode part, we have the anode and cathode. In order to study the electrical performance of the solid oxide fuel cells, for the electrolyte, we need almost pure ionic conductor, and for the anode and cathode, we need for the mixed conductor, which is that material can exhibit ionic conductor and electronic conductor. So this is the operating principles of the solid oxide fuel cell in hydrogen fuel. Okay, if we look at that electrolyte part, we have the oxygen ion conductor, and oxygen move from the cathode to the anode via the electrolyte. And you can see, based on the chemical reaction between these three components, for the solid oxide fuel cell, the water form at the anode side. Okay, if we compare to the oxygen ion solid oxide fuel cell to the proton solid oxide fuel cell, based on this operating principle, for the proton ceramic fuel cell, the proton moving from the anode to the cathode, and based on the, as a result of the chemical reaction, we found that the water form at the cathode side. This is the one of the differences between oxygen ion conductor and proton ceramic fuel cell. So when the water form at the cathode side, so it can avoid the dilution of the fuel. Okay. This is the direction of the proton ceramic fuel cell in the hydrogen as a fuel. If we want to study the factor that affects the efficiency of the proton ceramic fuel cell, of course we have to go on the electronic and ionic conductivity of the cathode and anode, and we have also to study the ionic conductivity of the electrolyte. So the next, I will briefly describe what we have done for the electrolyte and the anode and cathode part in order to enhance the performance of the PCFC. This is the materials that we use in our lab for the electrolyte part, which is a proton ceramic fuel cell. And this proton ceramic fuel cell actually can be operated at 400 to 700 degrees Celsius, which is we call as intermediate temperature range. In our lab, we use proton conductor of barium, cerium, zirconium oxide, and we dope with ytterbium. Okay. So why we use this dope barium, cerium, zirconium oxide in the for the electrolyte of our cell? Because this material exhibit can process a high density of the material, which is we can get around more than 95% dense of the electrolyte. It also shows the mechanical and chemical stability towards carbon dioxide and water vapor. and also it compatible with the cathode and anode materials, because we also want to fabricate the cell that consists of the anode, cathode, and electrolyte. And this material is well known as a proton conductor at the temperature ranging from 400 to 700 degrees Celsius. This is a few factors that are affecting the ionic conductivity. So we have to study on the sintering technique in order to get the dense material of the protons. And also we want to study what happens if we reduce the grain size from the micron to the submicron and until to the nano size of the grain. Okay, we also have research on the methods using sintering aids in order to get a more dense of material with a low sintering temperature. Okay. For the anode material in our labs, we use a cement, which consists of a nickel oxide BCZY, which is metal from the nickel, and ceramic comes from the barium, cerium, zirconium oxide. So this is the anode that we use in our lab. Okay. So again, in order to study the electrical properties of these anodes, we still use the, mostly we use the wet chemistry method in order to modify, to tailoring the structure or morphology of the materials. Okay, so because anode also one of the component part that important for the electrochemical reaction in the fuel cells, so we propose to study to use the anode composite nickel oxide BCZY that can improve the performance of the solid oxide fuel cell at the intermediate temperature. Okay. So based on these reports, okay, from the material reports, we can see that nickel-based cement anode, if you want to improve the morphology or microstructure of the anode to enhance the performance of the anodes, okay, we have the research on the mechanical processing. That one is under the fabrication method, and also we have the nano-scale structure, high TPB. In order to have the high TPB, we also have a few chemical agents, okay, to increase the TPB to produce the electrochemical reaction at the optimum level for the solid oxide fuel cells. Okay, so another one, not only for the hydrogen fuel. We also study on the hydrocarbon fuel. If we use hydrocarbon fuel, so what happened to the anode side, what happened to the performance of the single cells. And the last part for this component of the single cell is the cathode materials. Okay, for the cathode materials, we have the electronic conductor, mixed ionic electronic conductor, and also the composite cathode. So for our labs, our research, we study on the what happened to the performance of the single cell if we use the MIEC, which is in our lab we use lanthanum strontium cobalt ferrum oxide and barium strontium cobalt ferrum oxide. Okay, so after that, we also move what happened to the performance of the single cell if we replace the MIEC to the composite cathode. So for the composite cathode, we use the MIEC plus the proton conductor. So if we look at this slide, so in order for to study the cathode development of the solid oxide fuel cell, also we have to look on the performance of the single cell if we use composite cathode and also what happened if we modify the structure of the cathode into the nanostructure, or what happened if we use the, instead of use nanopowder, we go for the nanotubes. Okay? We also have one research when we substitute the nanopowder into the nanotube, so what happened to the performance of the single cells. Okay? So in terms of the cell configuration, after we study single material for the anode, cathode, and electrolyte, we go for the single configuration. There are three types of single configuration, which is anode supported cell, cathode supported cell, and electrolyte supported cells. But we focus more on the anode supported cell. This is the top view. This is the top view of our single cell and the side view of the single cell. In terms of the configuration, so we have the cathode functional layer, electrolyte, anode functional layer, and anode supports. So this layer we support on the anode substrate that contains of the nickel oxide BCZY. This is the technique we use for the cell fabrication. Okay, we use a dry pressing technique to make the substrate of the anode. After that, after we have the substrate of the anode, we use a spin coating technique to deposit the electrolyte on top the anode, and then the cathode on top of the electrolyte. Okay, this is the step that we use to fabricate a single cell of the proton ceramic fuel cells. This is the fabrication of the anode supported single cell. So how we, the summary of how we fabricate the single cell, which is under the anode supported cell. Okay, we use the dry pressing technique and also the spin coating technique. In terms of characterization, for this presentation, I just highlight on the button cell microstructure and also the button cell performance test. We go for the electrochemical study to study the conductivity of the material as well as the conductivity of the cells. And also we have 4-point probe measurement and SOFC testing station. That one is under, we send our sample or we run our sample at the Prince Songkhla University, Thailand. So this is the equipment that I use in our lab in UIT Perlis to conduct the button cell performance for the single cell that flow on the 10% hydrogen as a fuel. This is the summary of finding. Okay, for the electrolyte modification, we have modified the electrolyte behavior or the characteristic of the electrolyte by using chelating agent, surfacting agent, and dispersing agent. But for this one, I just present that we modify the microstructure of the electrolyte by using surfactants. Okay, we have used 3 types of the surfactant. Cationic surfactants, anionic surfactant, and non-ionic surfactants. From the various type of surfactants, we found that non-ionic surfactant, which is bridge 97, give the homogeneous morphology that we get the dense electrolyte at low sintering temperature. That's why from this result, we proceed for the next fabrication of the electrolyte by modify the BCZY using a surfactant, which is bridge 97. So based on this one, we have used 8 surfactants, and we found that bridge 97 is a good surfactants in order to get the dense electrolyte material at low acetylene temperature. And we study the performance of the electrolyte material using EIS, and this is the impedance study to show you the using of bridge 97 during the process of the electrolyte materials. For the cathode modification, to modify the cathode microstructure, we use dispersing agents. So in terms of the dispersing agent, we try to compare what happened to the microstructure of the cathode when you use activated carbon and ethylene glycol. This is how we explain the mechanism, the dispersing agent, how they disperse the particle during the processing process. And we also study we use impedance analysis to study what happened to the characteristic of the anode, of the cathodes if we use activated carbon and ethylene glycol. Okay, so we compare with the material without dispersing agent. So you can see that when we use activated carbon, the area specific resistance of the half cell is 0.3, and using ethylene glycol, the area specific resistance of the half cell is 0.2, which is much, much lower than the sample without any dispersing agent. We also modify the cathode structure in terms normal practice. We go for the nano powder. We also try to use the nano tube or nano rod. What happened to the electrochemical reaction if we use the powder in terms of the nano rod? What we prepare this nano tube or nano rod using the AAO template assisted solder method. Okay, so now we go for the impedance analysis, so we can compare what happened to the area specific resistance of the cell if we use the nano powder and nano rods. Okay, so you can see that by SAM and TEM, the one is the nano rod and the round is the nanospherical shape. Okay, and the below one is the impedance analysis for the nano rod and nano powder. Okay, if we go for the impedance analysis, if we use 100% of nano powder and 100% of nano rod, we can say that the ASR is higher. So, in order to get what is the best ratio to exhibit the high performance of the single cell, then we go for the ratio between nano powder and nano rod. And we found that if we use 10% nano rod and 90% nano powder, the cell will have the higher performance compared to the rest. In terms of the composite cathode, okay, we mix up between the LLCF and BCZY. We compare what happened if we use different ratio of LLCF and BCZY, which is MIEC and protonic conducting phase. Okay. After study on this three different composition of the MIEC and electronic conducting phase, we found that the best ratio is L7B3, means that 70% of mixed conducting electronic conductor and also 30% of the proton conducting phase. Why? Because if we use more conducting phase at the cathode composite, the water form, the amount of water formed is much higher that will lower the performance of the cell. Okay? So this is the impedance analysis to show what happened if we use different composition of the MIEC and electronic conducting phase. And if we go for the ASR, we found that L7B3 have the lower SSR compared to the L10BO. L10 means we use pure mixed ionic electronic conductor. And we also study if we use different cell fabrication techniques. Okay, we compare the performance of the single cell if we use a normal sintering process and we use triple roll milling process. Okay, so this is the proposed illustration that can show the calcine powder before process and the calcine powder after process, that we can break the agglomerate before we press the or before we layer the cathode on the electrolyte surface. So this is show the impedance analysis again to show you the resistance of the material that use the simple method. The below one is the simple method that have the higher resistance, and the upper one is the advanced method that give our lower resistance. So this is again the electrical performance based on the different preparation methods. For the anode modification, okay, we modify the anode using, we prepare the anode using EDSS method, one-step solder method, and two-step solder method. And also, we try to find what is the best reduction time to oxidize nickel oxide to become nickels. Okay? So this is the impedance analysis for the anode material that gone through the above mentioned preparation steps. Okay, so we can see that for the single cell, for this one, after we have modified the anode, modified the cathode, modified the electrolyte, we fabricate the single cell, and we go for the power density measurement, and in our lab, okay, until now, we can have the 300 milliwatt per centimeter square for our single cells. Okay. And also, we use the activated carbon to modify the microstructure of anode. So what happened to the performance of the single cell if we try to replace the anode that we use activated carbon to modify the structure of the anodes. Okay. This is again the impedance analysis that show you the area specific resistance of the cell that the normal anode which is without modification of anode, 77 ohm per centimeter square. After we use the anode that has been modified by the activated carbon, the activated carbon we functionalize. So we functionalize activated carbon first, and then we modify the anode, and we can get the polarization resistance is about 46 ohm centimeter square. So we managed to reduce the polarization resistance of the anode from the 77 to 46 ohm centimeter square. So in terms of the power density, but this one we just measure in the 10% hydrogen in our lab. Okay, so you can see that in terms of power density, the power of the anode that modified by functionalized carbon nanotube have the better value than the unmodified ones. Okay. And also we measure the polarization resistance of the single cell. This is the diagram that we use for the anode supported cell, nickel oxide modified BCZY. And this one, we also study what happens if we have the single anode functionalized layer and also single anode functional layer. So we also study what happens to the cell if we put this anode functional layer. This is the anode supported cell that I just mentioned just now. Before this, we just studied the anode in terms of size. The diameter is about 11.5 mm diameter. So we call it the first prototype from UITM PCFC research group. The performance of this single cell in 100% hydrogen as a fuel is about 311 milliwatt per centimeter square. So after we make the single cell and we try to study with it the single cell is working or not. So we found that this prototype is working. That show about 300 milliwatt per centimeter square. This is the cell that we use without the modification of cathode parts. After we modify the cathode part from the single MIEC to the composite cathode, so this one we use a composite cathode. The performance of the single cell, and now not working on the 11.5 mm diameter, we move to the 25 mm diameter of single cell. So the performance of this single cell with the modified cathode is about 400 milliwatt per centimeter square. So it's increased about 100 milliwatt per centimeter square from the single LSCF to the composite LSCF. Okay. So in progress now, we are moving also that material, that single cell, to working on the hydrocarbon fuels, because from the redox reaction, if we flow the hydrocarbon to replace the hydrogen, of course we will facing the serious choking of carbon at the anode site. Okay, so in order to study to prevent the choking of the carbon on the nickel particles, so we propose to work on the alkaline oxide and rare earth metal oxide. That's why in the coming progress, okay, we try to modify at the anode site. We put the layer of the rare earth metal oxide and alkaline oxide in order to reduce the carbon choking when we use the hydrocarbon fuels. This is our proposal on working on the hydrocarbon fuels. Okay, also we are in progress. Now we are working on the single cell. We are also moving on the stack cell. Okay, from the single cell, for the first step, we try to study on the two single cell. What happens if we stack the cell to become, we stack a single cell to become two cells and move to the 4 cells. That one, the work is in collaboration with ITB, Institute Teknologi Bandung, Indonesia. Okay. This is just the what we will do in the next future. Okay, we already imagine that this is the schematic diagram that we have to design in our lab to study the performance of the stack cells. Okay, This is the electrical performance measurement for the stack cells. So for the future interest and collaboration, of course, we also want to improve the current cell performance in terms of materials and technology of the processing and fabrication of the materials. We also need interest to study also in the interconnect development. For the interconnect development, we close deal with the UTHM, University Tun Hussein On, that they are familiar with the interconnect development. And the stack cell, as I mentioned just now, we are collaboration with the ITB Indonesia. Okay. So if you are interested to study on the material for the solid oxide fuel cell, you can join us under our group, Physics and Material Research Group, also, or another group is the Proton Conducting Fuel Cell Research Group. Okay, that's all for me. I'm really thanks to my University Technology Mara, my group, Physics and Chemistry Research Group, my society, MES, and my. Thank you very much for your attention.
Okay, thank you, Professor Nafisah, for the very informative and interesting talk. So we actually can see the revolutions of the proton ceramic fuel cells from the single buttons, 2 buttons, and then now the research team is actually working on the stacking of the button cells. Okay, so we shall now open for the Q&A sessions. So if you have any questions, you may raise up your hand and then introduce yourself, and you may proceed with the questions. So any questions from the floors? Anyone? Any questions? Any inquiries? Anything you want to ask Prof. Nafisah?
Hi, this is Han. That's a very nice talk. That I am interested in that the structure and also chemical stability. Do you have tried to improve the structural stability or chemical stability of your system?
Chemical stability.
Stability. Because of the fuel cell stability is very important.
Yeah.
Do you ever try to make the better stability?
We just study in, the stability, or up to now we just study the stability of the materials, not on the cell itself. For the material, electrolyte material, we have studied the stability of the material under the water vapor and also under the carbon dioxide. So we found that this material stable towards these 2 atmospheres. The one we, for the material, for the electrolyte material, we have studied the material, the stability of the material towards towards carbon dioxide and water vapor itself. But the stability of the single cell we not study yet. We just study the electrical performance of the material of the single cell based on the modification of our materials.
Okay, I think it's related to the question of Prof. Han is the shelf life of your cell. Have you done any measurement on the shelf life of your system? Whether it degrades over time? Does it degrade over time?
The degradation of the cells.
Yeah.
For the cell, actually, we now we quite new on the performance of the single cell. That's why for the single cell, we study more on the performance. Of course, we have to study the stability, the degradation of the single cell. Again, for the degradation of the material, yes, we study. We study what happened to the electrolyte material if we expose to the water vapor so long? Is it happen the gradation of the materials? Yes. For the material, we study the gradation, but not for the single cells. But the single cell is quite new. Before this, we spent a lot of time to study the materials, not on the single cell. But moving nowadays, we just moving on the single cell. That's why for the single cell, for the another characterization, the degradation, for the efficiency, for the repeatability, we not study yet. We still at the early stage of the performance of the single cells.
All right, thank you to Prof. Han and Prof. Halim for the questions. So I think...
Ada tu lagi.
All right.
Okay, Assalamualaikum. Okay, first of all, thank you, Prof, for the very interesting presentation. Okay, I'm Muhammad Sharifuddin bin Yahya from University of Malaysia, Terengganu. So actually, I was wondering, for your fuel cell, what is the operating temperature range? Because actually in UMT, we are from energy, solid state energy research group. So we are, normally we are releasing high temperature of hydrogen. So I was wondering if
How?
No, at the moment we are working on high temperature, so high temperature of hydrogen. It's because we are using solid state storage. So I just wondering for this fuel cell, so what is the temperature range? So maybe, I just want to know for how low temperature that we can reduce so that it can be fit to that fuel cell. Okay, thank you.
As I mentioned just now, if you're working on the solid oxide fuel cell, the conventional solid oxide fuel cell, normally operating temperature is above than 800 degrees Celsius. That's why our fuel cell, the operating temperature is from 400 to 700 degrees Celsius. Yes, we have the facilities and equipment to study the materials or the single cell or the half cell at this particular temperature range. But we just flow 10% hydrogen because we have the limitation in terms of flowing 100% hydrogen. That's why if we want to study the performance of the materials or the single cell at the 100% hydrogen, we send our sample to the Prince Songkla University. So they have the facility to measure the performance of the single cell in 100% hydrogen. Is it your question?
Thank you, Prof. Yeah.
Okay.
All right, so I bet that would be the last questions for these plenary sessions. So now I would like to invite chemist technologist Dr. Noor Hakimin Abdullah, the chairman of RCSSST2022 to present the token of appreciations to Professor NAFISAH. So please welcome. All right, thank you, Dr. Hakimin. And yeah, once again, thank you to Professor NAFISAH for the great supports to RCSSST 2022. So let us give a big round of applause to Professor NAFISAH. All right, ladies and gentlemen, so we shall now move to the second plenary speaker of RCSSST 2022. So first and foremost, let me introduce the second plenary speaker, Professor Dr. AZHAN HASHIM alias ISMAIL from University Technology Mara, UITM. Professor Technologist Dr. AZHAN bin Hashim alias ISMAIL is a professor in physics. He obtained a PhD in material science from University Putra Malaysia in year 2000. His areas of expertise is high temperature superconductor, HTS, and mainly focus on cuprate superconductors such as lithium barium copper oxide, YBCO, and bismuth strontium calcium copper oxide, BSCCO systems. So this research involved many fabrication techniques such as solid-state reactions, sol gel, and co-precipitations. So characterizations of these materials was carried out by SRD, SEM, FTIR, RMS, and ACS. So currently, he is working on computational methods for superconductor materials. He is a fellow of Malaysian Solid State Science and Technology Society, MAS, and was also appointed as council members of this society until today. He was awarded as Professional Technologist by Malaysia's Board of Technologies, MBOT, in 2019. He is active in research and publications. Professor AZHAN previously held the positions of Deputy Director of Research and Industrial Linkages from year 2009 to 2017 and Deputy Director of Academic Affairs from year 2018 to 2020 at UiTM Cawangan, Pahang. Currently, he is a Dean of Faculty of Plantations and Agrotechnology, UiTM Cawangan, Malacca, Jasin campus. So, ladies and gentlemen, without further ado, I would like to invite Professor Dr. AZHAN Hashim Alliance Ismail to deliver the plenary talk entitled A Study on Structural and Electronics Properties of Silver and Antimony Doped in Barium Site of Yttrium Barium Copper Oxide Superconductor via Computational Methods. So please welcome Prof. AZHAN. The floor is yours.
Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Thank you, Mr. Moderator, for your kind introduction. And first of all, I would like to thank the organizer for giving me the opportunity to share with you with our works on computational methods on superconductor. Okay, this is what I'm going to share with you today, a study on structural and electronic properties of silver and antimony dope in barium site of YBCO, which is 123 YBCO, superconductor by computational method. So this is a work done by my PhD student. She already finished her PhD last month. Technologist Dr. Siti Fatimah Sabudin. So I am the main supervisor, and the co-supervisor is Associate Professor Dr. Muhammad Faris at the back. So he knows very detailed on the computational methods. So we use his expertise to help us to understand what is actually happened in a YBCO or in a cupric superconductor in terms of copper oxide chain and copper O2 layer. Sorry, copper oxide chain and COU-O2 layer. Okay. Okay, this is the outline of my presentation today. So some background of study, problem statements, objective of this study, scope of study, research methodology, results and discussion, conclusion, and also recommendation. Okay, some background of this study is about superconductor. So superconductor is a material with perfect dimagnetism, which can expel all the applied magnetic field if we apply on this superconducting material, and has the capacity to conduct electric at no resistance. So that means it is resistanceless at superconducting state. And a low temperature superconductor, such as mercury, was found in 1911 by company Owens. It's about 4.2 Kelvin. And for high temperature superconductor, or HTHC, was found in 1986 by Bednos and Muller on lanthanum barium copper oxide, and the TC was 35 Kelvin. And for magnetically properties, type 1 BSC theory, type 1 we can explain using BSC theory, and type 2 superconductor still ongoing research. Right? So this is YBCO superconductor, 123. It stands for yttrium, barium, copper oxide superconductor, and the TC is about 93 Kelvin. So it also has another 124 YBCO, and the critical temperature is about 80 something, and also the 247. These three stoichiometry of YBCO system is quite established now. And so we will see what is actually happened on the copper and oxygen atom along the copper oxide chain at the bottom, and also at copper O2 plane that sandwich between yttrium, right? So this is some background of study for computational method. So we use first principle study and density functional theory for quantum theory that implement in the computational software code to calculate the properties of materials at atomic level. And material pseudo is a type of computational software for ceramic, metal oxide, polymer, nanomaterial, and etc. So example module or code inside this software is CASTEP, Foresight, Amorphous, etc. For this system, we use a CASTEP. And CASTEP computer mode is a module or code inside material pseudo software based on density functional theory. All right, so this is some background of DFT. So density functional theory is a quantum mechanical method for solving the electronic Schrodinger equation for molecules and crystal using a formalism that is based on the charge density rather than the wave function. So it is based on Schrodinger equation and also Hohenberg-Kohn theorem and Kohn-Shams formulation that we use this formula to develop or to make some correction for our computational method. And also for local density approximation, so XC, exchange correction only depends on density, and we use the generalized gradient approximation, GGA, which depend on density and its gradient. So some problem statements. So computationally doping impurities into a pure bulk sample using appropriate exchange correlation functional help to study the performance of the YBCO. So normally we did an experiment. So we measure the critical temperature, critical current density, and so on. But this one, we want to know what is actually happened beside the YBCO structure in terms of copper oxide plane and CuO2, CuO chain and CuO2 plane. So we previously there are many research on zinc, nickel, praseodymium, plumbum, lead, and gold doped into YBCO. Some concentration, it will improve the critical temperature and also the critical current density. So this research will be based, will refer to our previous research in 2013 on silver dope YBCO, which we found that it improved TC and achieved an optimal level of superconductivity when compared to other non-superconductive material. And also for antimony dope, it shows considerable structural modification upon doping. It changed from the orthorhombic to tetragonal if we dope beyond 0.3 of antimony. And some limitation, there is no research focused on the electronic properties of YBCO superconductor, especially when we dope with silver and antimony at the barium site using computational method. And this computational method is important to find the functionals that can be used to accurately model the properties of each material. So in CASTEP, there are many functionals that you have to choose which one is best fit with your experimental data. So later on, if we find out that this functional is work with our experimental data, so we can use if you want to modify it later, right? So previous theoretical study, structural and electronic property of HTAC in normal phase using local density approximation. So now we are trying to find out what is actually happened at the superconducting state. So previously, computational method was used at normal phase or normal state, which is not a superconductor state. And some limitation, calculation of strongly correlated structures in superconducting phase of YBCO superconductor. Okay, this is problem statement number 2. The electronic band gap obtained by computational calculation applying that standard DFT is much less than the experimental band gap. So limitation is insufficient treatment of electron correlation in system with strongly correlated material with localized D or F orbital. Hence, the density functional theory with Hubbard U with some correction method was developed to increase the size of the band gap and the predicting other properties. The limitation is not much is known on the performance of DFT plus U on the structural and electronic properties of AG and antimony. So when we dope, it must be some changes in the structure, in the CuO chain and CO2 plane, and also in terms of charge density. So number 3, the computationally calculated analysis and characterization of samples from experimentally synthesized material should provide correlation in explaining the intermolecular behavior, which resulted to the superconducting properties such as critical temperature Tc and critical current density Jc. So we try to correlate between this computational method with the experimental method and how it can increase the critical current density. All right, so first principle calculation have been performed on the Bravas lattice, the density of states, the band structure, and the Fermi surface topology for YBCO superconductor. And there are also some limitation because there is no available research focusing on the structural and electronic property of silver and antimoney dope at the barium side of YBCO using computational method that relates to the SDR experimental results. So this is the objective of the study, to determine the silver and antimony doping effect at barium side of YBCO by computational calculation based on its structural and electronic property using different exchange correlation. So we use LDA, CA-PZ, GGA-PBE, GGA-PBE Sol, and GGA WC. So we already found out that some exchange correlation is best fit with the experimental data. And number 2, to compare the structure and electronic properties of pure silver and antimony dope at barium side of YBCO superconductor obtained with standard DFT and DFT plus U with some correction. And number 3, to investigate the superconducting analysis of pure silver dope and antimony dope at barium side of YBCO obtained by the previous experimental method with the structural and electronic configurations obtained by first principle study applying computational method. So we compare between the computational method and also with experimental method. So the scope of study, first we have to, this is the crystal structure of YBCO. So the permeability, we use silver and antimony on barium side, and the probability is orthorhombic. And lattice parameter, A is equal to 3.831 angstrom, B is equal to 3.87, which is A is not equal to B because it is orthorhombic, and C 11.68 angstrom. The software we use is CASTEP method. We use DFT, LDAC, APZ, GGAPBE, GGAPBE Sol, and GGAWC. And also for DFT plus U, we use with some correction of U. And the properties, what we are seeing is for structure is lattice parameter, orthorhomicity, oxygen content, and also bond length. And electronic properties, we see the band structures, total and partial density of states, electron density, molecular population, and analysis. So this is the methodology. First, we have to build a crystal structure. We use this software. So when we compare with the experimental or with the previous structural, when we put all these elements, so it come out the same structure like before, which is we can see at the right side, in the middle is yttrium, the blue color, sandwiched with the CuO2 plane, and then a green one is barium, so barium 2, and above and the bottom one is the CuO2 plane, a CuO plane, right? A CuO chain, CuO chain. Okay. So calculation of material property with CASTEP calculation. So we find out the electronic properties and structural properties. Analysis for superconductor structure, and also we use electronic properties and structural properties developed by this computational method. Okay, so this is a methodology using DFT plus VCA. VCA stands for virtual crystal formation. So for one crystal structure for YBCO, it contains 1 yttrium, 2 barium, 3 copper, and oxygen 7. The total is 13. So virtual crystal formation, technically the simplest approach, allowing calculation on this ordered system to be carried out at the same cost as calculation for ordered structure. BCA ignores any possible short-range order and assume that on each potentially disordered site there is a virtual atom which interpolates between the behavior of the actual components. So this approach neglects such effect of local distortion around atom and cannot be expected to produce the final details of the disordered structures very accurately. So we have to make some correction to that. So this is a composition that we can use using this DFT plus BCA, which is not very accurate. And then we introduce DFT plus U, and we have to expand the cell into a supercell 2 times 2 times 1, where we can see there is a 2 crystal structure of BCO that on X it will expand because we use a 2 crystal structure. But for for Y and X, or B and C, remain similar. So we can see, if you use supercell 2 times 2 times 1, so we have to increase the number of atoms for yttrium to 4, barium is 8, copper 12, and oxygen 28, and it becomes 52 atoms in this supercell. So the advantage, we know that where we can put this dopant, not a half atom. So let's say if we want to put 1 atom of silver or antimony, so we have to use X 0.125. And if we want to put 2 atoms of dopants, so the X will become 0.250. That means we reduce the barium to 6, and so on. So with this advantage of DFT, so we introduce the DFT plus U to make some correction. Therefore, we can place the dopant 1 atom, 2 atom, and so on. All right. So for DFT, may not accurately calculate complicated many electron problems, and also not applicable to strongly correlated materials contain embedded localized 3D or 4F orbitals in extended SP state, causes complicated many electron problems not well be represented by LDA and GGA from DFT. The LDA and GGA methods delocalize electron across the crystal, resulting in each electron experiencing an average Coulombic potential. All right, so for DFT plus U, so denotes a Coulomb repulsion on site for localized D or F orbitals. Right, so it will be more accurate. Right? So provides a qualitative improvement over standard DFT, such as energy gap, magnetic moment, interatomic exchange parameter, and also introduce a self-interaction term analogous to the Hartree PROF terms to cancel self-interaction error. Okay, so first, before we start with this computational method, we have to do some conversion tests. The advantage of conversion test is to have more accurate calculation, to use computational time and cost effectively. And this is the selection of cutoff energy for the software. For copper, we set it for 400 electron volt, oxygen for 340 electron volt, yttrium 260 electron volt, barium 160 electron volt, and also for silver 300 electron volt and antimony 205 electron volt. So the selection of K-point sampling, we use a Mann-Hoss spec grid for YBCO. Okay, this is for single crystal. We can see that the cutoff energy is around 400 eV. This is the optimum cutoff energy for single crystal and also for the supercell, right? So for doped supercell, it requires more energy to converge. For these three, we use pure BCO, and then a silver 0.2 doped in barium, and also antimony doped 0.2 in barium for these three samples. All right, so this is a conversion test with respect of K-point samplings. All right. Okay, so result discussion for structural property of pure BCO. So we have experimental data, and also we compare with the computational method. So lattice parameter, this one from the experimental results. And automicity, oxygen contents is about 7 minus data is around maybe 7. So it depends. If the delta is more than 0.6, it becomes tetragonal, right? And then for bond length, so the bond length, like Cu1O1, Cu1O2, this is at copper oxide chain, and Cu2O2 at copper O2 plane. Okay, we can measure the bond length between copper chain and copper plane. All right, this is geometrical optimization using experimental. So this is the lattice parameter for ABC, and this is the correction factor, LDA, CAPZ. So this one, for pure YBCO, we can see that GAPB Sol, which is quite close. The close is GAPBE, but if we want to compare with the dope one, with the dope sample, so we use a GAPB Sol because the dope sample closely, the result is close to the GAPB Sol results, right? So we can see the difference in terms of A, B, C is less than 1%, right? All right, so this is YBCO lattice parameter. So we have some reference from 1 and from 10. Reference number 10, reference number 1. It's about these two experimental data use a solid state reaction method. And also we have DFT by previous competition studies. It remains autonomic, right? And then we have also the data for computational DFT and computational DFT plus U. We can see that the ABC is quite close to the experimental data, right? Okay, see this for dope YBCO lattice parameter using DFT, right? So GGA, PBA Sol is very close for AG, X equal to 0.2. And also for antimony, X equal to 0.2. And for DFT plus U, because we have to make some correction, so we can see that A is expand about twice for A because we use a supercell. If you want to find out what is the value for A, you have to divide by 2, right? Okay, same goes to the antimony, X 0.250. Because this one we use one atom at the barium site, right? Okay, this is the autorhomicity, right? Using DFT for 0.2 and DFT plus U for 0.25. So for autorhomicity, so in the autorhombic phase, when oxygen content increase, A and C lattice parameter decreases, and B lattice parameter increases. So as oxygen is incorporated to the lattice, it occupies either the O1 or O5 sites, increasing the length of the B parameter to 3.88 angstrom. The C parameter varies, it's about 11.84 for ideal tetragonal YBCO and 11.66 for the ideal orthorhombic YBCO. Okay, in the ideal tetragonal YBCO, the basal plane is free from oxygen ions, having A is equal to B is equal to 3.82, which is a tetragonal. Okay, this one, oxygen content of dope YBCO. So we use GGAPB Sol, which is quite close with the experimental data. It's about 10.24% difference. And GGPB Sol, 6.9, 6.9, so 7 minus data 6.9, it remains orthorhombic. And also for antimony 0.2, use GGAPB Sol, which is quite close. And also for the DFT plus U, 6.552, is quite close with the experimental data. All right, so as 7 minus delta decreases, so TC will increase. This is the oxygen content. Shows the superconducting quality of our BCO at range from 7 to 6.8 An increment of oxygen content from 6 to 6.5 allows the tetragonal semiconducting phase to be obtained. At delta is equal to 0.5, the phase transition from tetragonal to orthorhombic occurs. At 0.2, superconductive properties appear. And at 0, the structure is completely orthorhombic and superconductive, and the TC becomes higher than 90 Kelvin. All right? So we refer the referred experimental data is equal to 0.2. Oxygen content is about 6.8. So remain as orthorhombic. And antimony, because the ionic radius of antimony is very small compared to the barium, so it will shrink and the structure will contract and it's stressed to tetragonal, right? So this is the bond length. This is the between a copper oxide chain. So we focus on Cu1, O1 and Cu1, O4. And also for CuO2 plane at Cu2O2, Cu2O3 and Cu2O4. So you can refer with this diagram on the purple and also a yellow marker there. So when fraction of copper 3D electrons withdrawn from copper oxide plane, so copper oxide chain, so this one acts as a charge reservoir in YBCO superconductor. So Cu2O4, it indicates separation between chain and plane, right? All right, so for pure BCO bond length, okay, this is the theoretical value from Bezzoli et al. For Cu2O1, Cu1O1, for copper oxide chain, Cu1O4, and also for copper oxide plane, Cu2O2, Cu2O3, Cu2O4. And so apical oxygen between copper oxide chain and copper O2 plane, the distribution of all, it acts as a charge reservoir and copper oxide chain, and longer distance between copper oxide chain and copper O2 plane, less charge transfer, right? So this one for GGA, so you can see at copper oxide line, it shows a lattice order. So this one is for dope YBCO bond length for using DFT. So we found out that GGA BB-Sol is quite close, 1.9.46 angstrom. And then for DFT plus U is about 1.9 something. And then also for all dopant is between, it's around 1.9 angstrom, the distance of Cu1O1, Cu1O4, copper oxide chain. Copper oxide, copper oxide chain. Okay, so this one, the Cu1O1 bond length on copper oxide chain for Ag and antimony dope at barium side of YBCO superconductor. So we can see that as the dopant increases, bond length decreases because of attractive force between the atoms. And also for the Cu1O4 bond length, we found out that there is an abrupt change at x equal to 0.3. And you can see that in Ag it increased and in antimony it decreased due to the ionic radius of antimony is very small compared to the barium and silver. All right, so using DFT plus U, we apply in a supercell 2 times 2 times 1. And we use U is equal to 10 electron volt. So we can see as dopant increase, bond length increases, as bond length changes are smaller than antimony. So we can see the difference between the antimony and also with silver. Right? So this is what actually happened at copper oxide chain. And if you can see along XY plane, so bond length between Cu1O1 and Cu1O4 atom decreases away from barium and silver side. And at the right side, you can see the bond length between Cu1O1 and Cu1O4 atom decreases toward the barium and antimony side. And the bottom, along the YZ plane in antimony, you can see it shows a repulsive force between silver and in barium side with O1 and O4 atoms. And also for antimony dope shows attractive force between antimony in barium site with O1 and O4 atoms. Okay, so for dope WBCO bond length in CuO2 plane, okay, this is all the data, is about 1.9 in Cu2O2 and Cu2O3, and for Cu2O4 is around 2.7 angstrom for both dopant. Okay, so this is what is actually happened at a CuO2 plane. At Cu2O2, bond lengths on copper oxide plane of silver antimony dope at barium site of YBCO superconductor. So you can see as dopant increases, bond length increases steadily until x equal to 0.3. And for Cu2O3, bond lengths on copper O2 plane for silver antimony dope at barium site of YBCO superconductor. For antimony, as dopant increases, bond length decreases until x equal to x larger than 0.3. So it determines width of crystal structure. Right? All right, so in CuO2 plane, for Cu2O4, bond lengths on copper O2 plane for silver and antimony dope at barium sites. At Cu2O4, it separates between CuO chain and CuO2 plane. As dopant increases, Cu2O4 decreases and shows a decrement lattice parameter at y-axis. Right? On the right side, as dopant increases, crystal structure at YZ axis compress inwards antimony and small structural changes due to antimony. Right? Okay, this is for CuO2 plane. We look at Cu2O2, bond length on copper oxide chain for silver and antimony. And we found out that as dopant increases, bond length decreases, and for silver, bond length changes are smaller than antimony. Okay, antimony because of the unit size very small. All right. On the right side for Cu2O3, bond lengths on copper oxide chains for antimony and for silver antimony dope at barium site. So this is the range of bond length. It's between 2.01 angstrom and 1.83 angstrom. All right, so this again at Cu2O4 bond length. Okay, we can conclude that as dopant increases, bond length increases. Okay, this is what actually happened at CuO2 plane. Right, so we can see the bond length between Cu2O2, Cu2O3 and Cu2O4 atom decreases away from barium and silver side along XY plane, and bond length between Cu2O2, Cu2O3 and Cu2O4 atom decreases towards barium and antimony side. So along YZ plane, it shows a repulsive force between antimony and between silver and in barium side with O2, O3 and O4, and shows attractive force between antimony in barium site with O1 and O4 atoms. You can see the diagram there. Okay, so we want to validate on structural properties obtained by computation. These are experimental results with pure. DC is around 86 Kelvin. With JC is around 6.17 ampere per square centimeter at T equal to 70 Kelvin. And for silver 0.2 is around 87 Kelvin. The TC, JC is about 16.5, which is higher than the pure. And for antimony, 0.225, I suppose, TC is around, sorry, antimony S0115, TC is about 85 Kelvin, and JC around 2.75 angstrom. This one is related to the charge density between the CuO chain and CuO2 plane. This one is from rate refinement of SRD patterns and activity measurement. So we can see that lattice parameter, experimental and computational analysis using DFT and DFT plus U technique differ only by 5% in terms of lattice parameter. And autonomicity and oxygen content follow values obtained by lattice parameter. Right? It's not much change. So bond lengths, significant changes were observed along the C1O4 and Cu2O4 bond that connects the charged reservoir at the CO2 chain to the conducting CO2 plane for AG and antimony dope samples compared to the pure sample. So as the AG and antimony dopants were incorporated into the sample, it shows a decrement of silver and increment of antimony in the Cu2O4, right? And decrement away from barium and silver side towards barium and antimony side in the Cu1O4. Item separation, contraction due to the addition of impurity at barium side of the crystal structure. And the radius of silver is around 126, which is quite close with the barium. And antimony 76 is very small. When substituted into barium 134 picometer. And the bond length between copper 3D and oxygen 2p atom along the CuO chain and CuO2 plane contributed to the electrical conductivity, which results in increment or decrement of critical temperature Tc and critical current density. This one is the correlation between the electrical conductivity when we compare with the bond length. Okay, so bond length changes in the AG dopant less than antimony dopant crystal structure. Okay, so from experimental you can see for antimony beyond the 0.3, it changed from orthorhombic to tetragonal due to its size of dopant. All right, so result question for electronic properties of pure antimony, pure silver and antimony. Moderator, how many time I have? 1 minute more. I have many slides, so I try to go faster. Okay, this one is electronic properties. We want to see the band structure, which actually happened to the superconducting material. All right, so band structure between conduction and a valence band, there is a band gap. And density of state, we try to find out the density of state for each element. And then for electron density, so we can calculate what is the electron density at copper oxide, CuO chain and CuO2 plane, and also for the molecular population. Okay, this is a band structure for insulator. There is a large energy gap between valence band and conduction band. And for semiconductor, the conduction band is empty or partially filled, right? And then for metal, there is overlap. There is no energy gap. And then for the superconductor, we have a normal state, okay, at the left side. And also at superconducting state, we still have an energy gap between the conduction and valence band. Okay, so this is the previous experimental study. Energy band gap for pure BCO is around 4.8, between 4 to 4.8 electron volt. Okay, so we use exchange correction functional for this study, LDA, CAPZ, GGA, PBE, GGA, PB Sol, and GGA WC. So we find out in a DFT method, the energy gap is around 3.3 electron volt. And then for DFT plus U is around 3.75 electron volt. The difference for DFT plus U is only 8.25% when you compare with experimental method. So this one is the band structure using DFT. So we see that at E between negative 15 electron volt to 15 electron volt, the oxygen 2p and due to oxygen 2p and copper 3d orbitals, and at E between negative 9 electron volt to negative 7 electron volt shows covalent bond between O2p and copper 3d. And lowest conduction band CB at 7 electron volt. At the bottom side is the conduction band. The lowest one is the valence band. Highest valence band at negative 9 electron volt below Fermi level due to oxygen 2p electrons. Right? So this is DFT for AG dope. You can see that band gap between valence band and conduction band decreases to 0. We cannot see that, it is overlap. So therefore, for DFT, the energy gap is is only 0 electron volt. And maximum width of valence band move towards EF hybridization between O2p and copper 3d electrons. And then for antimony, the band gap between a valence band and conduction band decreases to 0. And for X equal to 0.25, the energy gap is around 0.28 electron volt. Okay, this is, we use a DFT plus U. We can see it clearly because we use a supercell. So energy band gap more concentrated at energy, Fermi energy, hybridization between O2p and copper 3D electrons, and also the Van Hoff singularity, VHS, and also dose. And there is a band gap correction of 2 DFT applying disordered crystal approach in VCA. So we use DFT plus U, where U is equal to 10 electron volt, and the largest band gap we found that is 3.7 eV. All right, so this is the DFT plus U in a dope or BCO. You can see the energy gap clearly. Okay, so density of state, variance in band gap due to difference in density of state. It will, so that we can know what is the number of electron occupied states per energy level interval. For high density of state means that many occupation states are possible at that level. And zero density of state, that means no state can be occupied at that level, and partial density of state, overall density of state contribution to several angular components for the atom in the system. And this is the basis of balanced state for the atom. Yttrium is contributed by 4D, barium by 6p and 5D, copper by copper 3D, oxygen by oxygen 2p, and silver by 4D, and antimony by 5p. All right, so this is the density of state. The valence band mainly contributed by barium 6p and oxygen 3s. And for the conduction bands, mainly contributed by the copper 3D, oxygen 2p, barium 6d, and yttrium 4d. Okay. All right. How many times?
Actually, time's up already.
Oh, finished already. Okay.
So maybe you can come.
All right. So basically, so I go to the conclusion, just to, because there are many slides. It's about 60 plus. It's very detailed. Okay, this is about the electron density. So from this computational method, we can see the electron density at each atom, right? Okay, this is at the CuO plane, copper oxide plane, and also at CuO2, CuO chain and CuO2 plane, right? We can calculate what is the electron density at this plane and also chain. Right? Okay, so I go to the conclusion. All right, so silver and antimony doping effect applying different correlation functional. So on structural properties, the lattice parameter using the FT shows antimony and silver represented of at x between 0 to 0.3. The difference is only 5%. All right, so it's explain the improved conductivity upon silver doping and structural modification of antimony doping. Okay, and on electronic properties, the band gap for pure is about 3.3 electron volt, and for the silver is around 0 if you use a DFT method. Right, so the total and partial dose along copper oxide chain and to plane increase after dope with silver antimony in singular in crystal structure. All right, so this is when we compare with the DFT and DFT plus U for structural, we can see that both the difference is only 5%. Right, and then for electronic properties, the band gap DFT plus U for pure is about 3.67. Okay. All right, this is the recommendation. So thank you very much.
All right, thank you to Professor AZHAN for the very informative and interesting talk about the usefulness of computational modeling, which is DFT, density functional theory, DFT, and DFT plus U for the developments of the superconductor. So ladies and gentlemen, I think since we are running out of time, so if you have any questions, so you may approach Prof. AZHAN later on. So now I would like to invite chemist, technologist, Dr. Noor Hakimin Abdullah, the chairman of our RCSSST2022, to present token of appreciation to Professor AZHAN. So please welcome. All right, thank you, Dr. Hakimin, and once again, thank you to Professor AZHAN for the great supports to RCSSST2022. So let us give a big round of applause to Professor AZHAN. All right, ladies and gentlemen, so we shall now move to the third plenary speakers of RCSSST2022. So first and foremost, let me introduce the third plenary speakers, Professor in Senior Technologist Dr. AHMAD Sulaiman from University Malaysia Kelantan, UMK. So Professor in Senior Technologist Dr. AHMAD Sulaiman is currently a Senior Director for Research Management and Innovation Center, RMIC, University Malaysia Kelantan. Professor ZIAD holds a Bachelor's of Chemical Engineering and Master in Chemical Engineering from University Technology Malaysia, and a PhD in Biochemical Engineering from Massey University, New Zealand. He has published extensively in the areas of separations, biochemical processes, sonobioreactor technology, enzyme technology, microbial fermentations, herbal extractions technology, and bioreactor design. His more recent projects have focused on classical and novel approach to the analysis of honey and detections of adulterants and kinetic correlations of gas-liquid mass transfer coefficients and oxygen uptake rate of heterogeneous protein cultivations by sonobioreactor. His impressive background both in research and academia landed him several prestigious awards, which includes gold medals in Carnival Research and Innovation, CRI UMK, in 2019, gold medal and Best Award, Inventions and Innovations Award at Malaysia Technology Expo, MTE 2019, gold medal, gold award, and the Best of the Best Award, Educationals and Institutions, at the International Inventions, Innovations and Technology Exhibitions, ITEC 2019. In recognition of his numerous contributions to the broad field of chemical engineering directly and society indirectly, he was the recipient of several honors and awards, including the Pingat Setia Ahmad Shah Pahang, SAP, in 2006, Pingat Jasa Kebaktian PJK in 2009, and Pingat Kebaktian PK in 2012. So ladies and gentlemen, without further ado, I would like to invite Professor in Senior Technologist Dr. AHMAD Sulaiman to deliver the plenary talk entitled Use of Ultrasound in Enhancing Productivity in Biotechnological Processes. So please welcome Prof. ZIAD. The floor is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And very good morning. Salam keluarga Malaysia. Thank you very much to the Dr. Teo for your kind words. And all of the participants, thank you very much. You still be here. Okay, just to concentrate, focus for the knowledge sharing by the presenter. Okay, today I would like to sharing some of the part of my research, use of ultrasounds, the importance of ultrasound in biotechnological processes. Biotechnological processes we can divide it by two. One in the microbiology, microbial fermentations, and some other parts is enzymatic hydrolysis. Okay, and then basically this is related to the solid particle as well. Okay, because of today, this morning, still morning? Okay, this afternoon, I will try to share with you guys the relations between the ultrasound and soluble and insoluble particle cellulose. Okay, how actually the sound is actually can can enhance the process, can enhance the product, especially for the bondings of enzyme and the substrate. Okay. What is ultrasound? Okay, I think this is a quite very interesting topic. I did my bachelor when I did my FYP. Okay, now we call FYP, Project Final Year, or the capstone project. I did my FYP also in ultrasound. How I improve the flow rate of the membrane using the using the ceramic membrane filtration. During that time, I'm using ultrasound. And then when I move when I continue my masters, and then also I did in ultrasound as well. But how actually I can increase the production of the palm oil, okay, in the palm oil industry. I'm using ultrasound as well, okay. And then when I moved to when I planned that I need to continue my PhD, and then during that time I just advised myself try to avoid from ultrasound, okay. Why you still need to do ultrasound? But no, because of when I went to the New Zealand, okay, because of they have really abundance of the lactose, because of the New Zealand they have a lot of the milk waste and so on, and then my supervisor asked me to continue how actually the ultrasound can improve, the production of ethanol, for example, okay, based on the lactose waste product and so on. Basically, during my PhD, I'm not just only doing the microbial fermentation, but I'm doing the hydrolysis, the enzymatic hydrolysis, and then related to the mass transfer coefficient. Okay, because of my background is a chemical engineering, and I need to do at least some parts of the engineering background and so on. Yeah. All right, what is ultrasound? Sound is actually a frequency is more than 20 kilohertz. That's why we and the N, N? Semut, okay? We cannot talk each other, okay, because of the difference of the frequency, all right? But if our frequency is the same, you can know what is actually the N try to talk about you, all right? Then of course, if they say bad about you, and you will step them straight away. All right, that's why this is the miracles of the wave. Basically, birds they have their own frequency, and they have their own frequency, and because of the human itself, they have the frequency is more than 20 kilohertz. This is the important because of at 20 kilohertz, this is actually inaudible to human ear. That's why we can talk each other. All right. Otherwise, because of sound is actually energy. Is the energy getting produced when it vibrates, okay? It's like our, what we call this one, trachea, right? Okay? When we talk, and then we can see sounds, and then we can hear about voice and so on. Okay, sound is actually widely used in non-biological sonochemical processes. Okay, of course. I promote this ultrasound as well in your solid state study in the physics background and so on. Yeah, but such sonication regimen are not acceptable for biotech processes. Okay, I think from the previous history, always people say that ultrasound can use just to denature the enzyme, to kill the protein, to kill the enzyme and so on. But they are noticing that they have the positive output that we can apply using the ultrasound can improve, can enhance the process of the biological or non-biological process. Yeah? At high intensity ultrasound, it's known to damage the cell and enzyme. Yeah? But based on my study at low power, intermittently applied, 1 second on, 9 seconds off, 1 second on, 9 seconds off, meaning that there is the percentage, the 10% of the sonication application. Okay, ultrasound has the potential to improve the productivity of the biotech processes involving the live cell, cell-free homogeneous enzyme catalysis, and cell-free enzyme catalysis system with solid substrates. Okay. All right, how can ultrasound improve the processes? You need to ask yourself. And then I did my PhD up to 5 years. nearly 5 years. Okay, it's not easy because of, I think maybe some of you, you graduated on time, 3 years and so on. But for me, I still need another more 2 years because of I need to learn more about the biotechnology. Because my background is purely in chemical engineering, and then always my supervisor said, you need to know about the cellulose and cellulase. Always during my first year, I'll always confusing between the cellulose and cellulase. Right? And then my supervisor said, you go back to the first year in this university, go to the class, take the subject with the first year student, and you learn what is a cellulose and cellulase. And then I need to spend another 1 more year, okay, with the undergraduate student before I continue my PhD in New Zealand. How, you see? This is quite interesting. All right? Okay. How can ultrasound improve the bioprocesses? This is based on the possible mechanism at the constant temperature of operations. Yeah? Enhanced gas-liquid mass transfer. For example, for the aerobic fermentation, which is the biomass and ethanol production by the K. marcianus from lactose. Okay, enhanced solid-liquid mass transfer, which is the enzyme system involving solid substrate. For example, the hydrolysis of insoluble cellulose by cellulase. All right, cellulase is an enzyme. Yeah? All right, and then directly influence cell metabolism by inducing intracellular motions using the life cell system. Okay, for example, K. marcianus, and directly influence enzyme substrate binding and unbinding in a homogeneous enzyme catalysis system, for example, lactose hydrolysis by beta-galactosidase. But I'm not sharing with you guys for all the 4 topics, but I just need only to concentrate only for the particle topic. How actually the ultrasound improve, okay, the unstable with the stable cellulose using the ultrasound. Yeah? Okay. Ultrasound, actually, this is continued. Ultrasound can induce the microturbulence at interface and in the bulk fluid, enhance the mass transfer. Okay, I think most of you know about the mass transfer, right? Between the 2 pieces of equilibrium system, which is we have the gas liquid and solid liquid, all right? And then the coefficient is actually the things that to measure, okay, what is actually the quantity used during the equilibrium during the equilibrium stage. Yeah. Okay. The second one is reduce gas bubble size and increase gas hole up, enhance the interfacial area for mass transfer, and may cause intracellular motion and cell vibrations, and induce the breakup of flux, improve mass transfer without the damage to the individual cell. This is more on the information about how actually the ultrasound can improve the process, can enhance the process. Yeah? Okay, the objective of the research, this afternoon I just only focus and concentrate just only for the hydrolysis of various soluble and particulate cellulose by the enzyme cellulase, a model system involving solid liquid mass transfer. Okay, because of, I know most of you is actually expert in the solid, and most of you is expert in the particle. And then we try to see how actually the particle and the soluble and insoluble particle can produce a very good product. Why we applying with the ultrasound? Yeah. Okay. General experimental approach. Okay. The first experimental approach that we characterize the kinetics of the processes under various sonication regimens. Okay, when you talk about ultrasound, you need to put it the regimen. Regimen means that the conditions, yeah, including the control. Control means no application of sounds. Yeah. Okay, just to cellulose, for the cellulose hydrolysis to glucose by cellulase, for the soluble cellulose, for the particulate insoluble cellulose of different sizes, cellulase denaturation under different sonication regimen. Okay, this is like a small part of my research. And then I have too many parts as well. Not just only for the lactose, and then we're studying for the high gravity of the substrate. The high gravity means that the high concentration of sugar, okay, glucose, okay, for example, up to 100 kilogram per liter concentration. Okay, how actually the microbe can live in the high concentration of sugar, and when we use the ultrasound, it can help the the process to produce more ethanol and reduce the production of CO2. Yeah, all right. The general experiment approach number 2 is using above data, identify the possible causes of process enhancement by sonication. For example, in contributions of solid-liquid mass transfer, okay, enhance the enzyme substrate binding and unbinding. Okay, I think most of you know about the catalysis before, right? And then the use of the enzyme or the use of the catalysis is to binding the one substrate to the enzyme. Okay, when they have like a really good binding among them, they can produce more product at the end of the process. Yeah. All right. This is the schematic of the sono-enzymatic system. I think most of you are quite familiar with the middle equipment. That one is a fermenter, okay, or the bioreactor, okay. And then I tried to modify that so that the liquid can flow in out, okay, using a peristaltic pump, and then go to the ultrasound chamber, okay. Basically, we actually why we put the ultrasound chamber outside because we did not want, okay, the ultrasound will be disturb, okay, the condition of the bioreactor ecosystem in the bioreactor. Yeah. Okay, this is the details of ultrasonic flow cell dimensions in cm. Okay, then you can see that where is the sonotrode, where is the gap, where is the space that the liquid can go in, and then attach with the sonotrode, and then the sonotrode apply the power, and then they go back to the outlet, and then the outlet will go back the treated product will be go out and then back to the fermenter. Yeah. Okay. The materials and method. Okay. For the soluble and for the soluble and insoluble cellulose to produce the glucose. Okay. For the soluble we use the Accelerase 1000, which is genetically modified from the strain derived from the T-raceae. Okay, the activity of the enzyme we fix at 2,500 unit CMC per gram. Okay, and then we run the experiment in the batch process, which is at the 50 degrees Celsius, pH at 4.8, and then the RPM for the stir is 500 RPM. The CMC soluble cellulose model system. Okay, this is all about the condition. Okay, without ultrasound is control. And if you can see the various characteristic application of ultrasound, we use at 10%, 20%, 40% duty cycle, meaning that 1 second on and 9 seconds off. Okay, that is what we call the 10% of sonication. At 3 intensity power, okay, and then when we talk about the ultrasound, you need to know about the frequency, you need to know about the power, and then you need to know about the duty cycle. Yeah? And then for the power, we use a 3, 6, and 50 watt, corresponded to the intensity 2.4, 4.7, and 11.8, respectively. Yeah? Okay, this is for the insoluble. We use the Solca flock, okay, and then the same condition, all right. For the enzyme stability, we need to check for the enzyme stability as well without the buffer, and then whether the enzyme can stay, can working in the tested sonication regimen that we propose. Yeah, all right. For the measurement, I think it's quite straightforward. For the glucose concentration, we're still using the YSI fixed enzyme sugar analyzer. Okay, instantly boil in the boil water, 100 degrees Celsius for 10 minutes to inactivate the enzyme. Okay, after you finish during your harvesting your sample, and then immediately you immerse it into the hot boil water. Okay, just to make sure that you denature or you kill the enzyme, and then you can check for the glucose production. Okay, centrifuge at 2415 G-force for 10 minutes and do for the enzyme assay. Okay, this is the schematic of the hydrolysis reactor system and sonotrode. This is the arrangement that I did in the lab before. Okay, just to make sure that that's easy can control and then easy to do the enzymatic hydrolysis. Yeah? All right. The result in discussion, we just focusing on the hydrolysis of particulate and dissolved cellulose powder by cellulase to glucose, which is we demonstrated the contribution of sonication to possible enhancement in solid liquid mass transfer and hence the rate of hydrolysis including control. Okay? For the soluble cellulose, for the particulate insoluble cellulose of different sizes, and the cellulase denaturation under different sonication regimen. Okay, if you can see here, this is the glucose production from the hydrolysis of CMC with accelerase 1000. I think this is the for the y-axis for the glucose concentration that we did from the experiment, and at the time, if you can see that, okay, the most producing of glucose is actually at a 40 gram per liter of concentration. Yeah, if you can see that, I think this is like a really nice smooth graph. And then when I draft this, when I plot this kind of graph, is quite tough as well. Not just only do for one experiment. I think for the one line, I did almost like 9 or 10 times of experiment. And then to run for the one time of experiment, it takes you about 12 hours, nearly to 24 hours to run, right? And then this is only for batch. And then for during my study, basically I need to run for the fed batch and continuous as well. Continuous up to 3 months to 4 months. That's why at the beginning of my speech just now, I can't settle my PhD up to 3 years, but I need to extend up to 5 years. Right? This is just only for one topic. Okay, I still have another two more topics that I need to, because basically the huge of data lah, heaps of data. Okay, this is for the double reciprocal line Weaver bulk 1/V versus 1/S plot for enzymatic hydrolysis of lactose, just to determine the VM value and the KM value. Okay, the VM value is the maximum reaction rate, and then KM is the enzyme, the Michelis maintain, which is represent for the enzyme use, meaning that we need to have like a really good higher VM, okay, with the less KM. That is the objective, meaning that when you produce something like a product, you just need you will need the more product, but really less of what? Of material. That is an example. Okay, this is the, of course, to draw these kinds of graph, it can feel something like crazy as well. Because of my supervisor said, if you cannot get 100% or nearly one, you need to repeat. That's why when I heard from somebody say about repeat, I'm really blur, you know, because the word repeat is nightmare for me. Yeah? All right. Okay, this is the effect of ultrasound on the hydrolysis of CMC by cellulase. If you can see here, this is a part, okay? If you can see at the x-axis is the sonication duty cycle, which is we just now we mentioned about the control. We have the 10% application, 20%, and 40%. If you can see from the VM, from the maximum reaction rate, we determine that at the 10%, at very short sonication cycle, 1 on, 9 seconds off, okay, it's actually very beneficial for the process, which is at the 15 watt of ultrasonic, okay, ultrasound application, it can give a very optimum production rate. And then compared to the KM is the enzyme that we use. Of course, at the 10%, okay, at the power at 15 watt, okay, it gives like a really less KM value, okay, based on the specification or the tested sonication regimen that we applied for both for the CMC by the cellulose process. Yeah. Okay, this is effect of ultrasound on insoluble cellulose, which is the non-soluble at different particle size. Okay, this is if you can see the graph. The left graph is a control. The right graph is with ultrasound. Yeah? And then if you can see that we tested the different insoluble particle, the Solka flock at 30 micrometer, at 60 micrometer, and 290 micrometer. And then you can see the pattern. Okay, the pattern meaning that if you use a very small particle, they can give like a really produce more glucose production. Meaning that if you go more particle size, a large particle size, they're not giving you much glucose production. Yeah? Okay? This is the effect of ultrasound on residual enzyme activity without presence of substrate at different level of duty cycle and power intensity. And then based on the study, we can see that at low intensity, at 2.4, they will not give a bad impact on the denature of the enzyme. Okay? If you can see the top 100% is actually a control enzyme, and then if they go down to the 100, basically the enzyme is slightly denatured or slightly killed. Okay, slightly denatured lah, denatured enzyme. Okay, I think for the conclusion, all right. In the hydrolysis of soluble and insoluble cellulose, the hydrolysis followed the Michaelis-Menten kinetics without inhibitions, and then the kinetic parameters of the hydrolysis reaction were estimated by the direct linear method of Lineweaver-Buck plots. Okay, and then in the hydrolysis of soluble cellulose, ultrasound enhanced the VM and reduced the Km under optimal condition, which is a 10% duty cycle, which is 1 on and 9 seconds off, and power intensity of 11.8 watt per centimeter squared, relative to control, which is with no sonication. Using the optimal sonication, the maximum reaction rate was nearly double relative to control. All right. In the hydrolysis of insoluble cellulose at different particle of sizes, okay, at smaller particle size, 30 micron, ultrasound degraded the crystallinity of the cellulose, yielding 1.1-fold of glucose relative to control with no sonication. And last but not least, the activity of cellulase in substrate-free buffer with sonication showed that its activity was almost unaffected by ultrasound and was lost its activity 20%, nearly 20% under optimal condition, which is at 10% duty cycle and power intensity of 11.8. This is based on the tested regimen that we use in the process. Meaning that we appreciate actually when we use ultrasound in our process, we can enhance. Okay, we can enhance the process, especially in enzymatic hydrolysis, in the microbial fermentation as well. Okay, basically we try to tackle the negative, the negative say by the other researchers saying that when you use ultrasound, you will kill the cell, you will damage the cell, you will denature the enzyme. Okay, meaning that I prove that with this kind of research, with these kinds of output and findings, the ultrasound is actually better to enhance or to improve the process in biochemical and the chemical processes. Without that, thank you very much for your attention. Assalamu alaikum.
All right, thank you very much, Professor ZIAD, for the very informative and interesting talk. So usually when we talk about ultrasound, so as material scientists, we use the ultrasound for NDT, non-destructive test. So maybe for the medical scientists, they use it for the ultrasound devices. But I think with these sharings, we actually gain a new insight, a new knowledge on the usefulness of the applications of ultrasound for the biotechnological process, so the chemical processes as well as the biochemical processes, right? So next, maybe we shall move to the Q&A session. So any questions from the floor? All right, please welcome.
Test. Assalamualaikum, Dr. ZIAD. Congratulations. Very good presentation. You didn't mention about the frequency used in your study. So Can you enlighten us on the frequency used, the frequency of the ultrasound?
Okay, thank you very much. Based on the, what's your name just now?
Dr. Nazlim, sorry,
Okay,
from
Dr. Razif
UKM.
from?
UKM.
Okay, you can. Thank you, Dr. Razif. I think based on your question, that's why just now when we talk about the ultrasound, we have three things, right? Three important things. We have the frequency, we have the duty cycle, and then we have the intensity. Okay, intensity means that when we go somewhere, for example, when you go by bus, for example, if you have more passengers in the bus, for example, and then the bus moving is slightly slow. That is the definition of intensity itself. I think for the frequency, okay, basically you can use other number of frequency. For example, because of why we use the 20 kilohertz, because of we can hear. We can use because of if you learn about the physics, like wave is actually can produce two types of wave. One is longitudinal wave, and then another one is transverse wave. Okay, meaning that the frequency is actually 1/t, for example, 1/t. If we learn physics before, right?
The frequency used in your study.
Oh, my frequency in the study. Okay, during my study, I fixed my frequency at 20 kilohertz.
20 kilohertz.
20 kilohertz, because of we noticed that at up to 20 kilohertz, basically based on the literature, most of the process happen very well during at the 20 kilohertz.
So
Yes.
why did you choose 20 kilohertz? Because 20 kilohertz is at the boundary of between detected sound and undetected sound.
Okay.
So why did you choose in the first place 20 kilohertz?
Okay. Basically, I did my literature during that time, okay? And then, of course, if we need to do the optimization study, we tested up to the boundary of 20 kilohertz and the low boundary of the 20 kilohertz. Basically, it will take more time because of you just not only running only for one characteristic of experiment, but you have a lot. You have the batch, you have the fat batch, and then you have fermentation. What we do is actually based on the literature found from the literature, the 20 kilohertz, we use the 20 kilohertz because of the 20 kilohertz is the ideal frequency for the fermentation and enzymatic hydrolysis process.
So you have a reference for that? Is it?
Yes, I have the reference, and then many of the reference is from the sonochemistry journals and whatsoever.
Okay. Well, are you expecting any changes if you use if your study is conducted at higher frequency, at megahertz frequency,
Yeah,
for example?
I think that is quite interesting question because of based on my recommendations for the future recommendation study. Basically, that's why I mentioned just now, you have the high intensity and low intensity at 20 kilohertz of frequency. Meaning that if you go your experiment up to high intensity, because my study...
High frequency.
High frequency, yeah. Because
frequency.
when you go up to the high frequency, basically the damaging of the cell is very, very bad. Okay, because of the when you use that, because of right, when the transverse wave, when you go for the high frequency, and then the cycle will be rapidly close each other. Okay, basically they will give like the really bad damage or really bad result to the process of the system.
Okay. Can I ask one more question?
Yes.
During your work, your experimental work, did you notice any cavitation? Cavitation, the formation of bubbles.
Okay.
Did you notice any cavitation effects?
Okay, I think that is another good question. Yeah, because of like during my study, they produced the bubble, the really micro tiny bubbles. Put at the end of the sonotrode. All right, and then during that time, that's why I have something effect to my ear until now because of I just had my vertigo last 2 months ago. This is affected by the really long exposed to the sound before. All right, and then one of the things basically when you run your experiment, you can see the really tiny bubble, there is a collapse in the liquid. Basically, that's the definition of the vibration. It actually is the collapse of the tiny bubble because of the expansion and extraction of the bubble, and then they produce that really high intensity of energy.
So
This energy can give like a physical effect to the process.
So how do you overcome? It could deteriorate the results, your expendable results. So how do you overcome the cavitation effects in your
Okay, that's why I'm not studying the behavior of the tiny to the sample. Okay, what is I just play around with the sonication cycle, meaning that sonication cycle means that we expose just only 1 second ultrasound, zzz, and then we stop at 99 seconds, meaning that rather than we just apply continuously, zzz, okay, forever, for example.
So you mean you were using the pulse ultrasound?
Yeah, using the intermittently pulse, meaning that
pulse, not the continuous type of wave.
Yeah, meaning that they give a really good beneficial to the system, to the process, when we apply intermittently, meaning that 1 second, 9 seconds off, 2 seconds, and 8 seconds off, something like that.
Okay, thank you very much.
Thank you very much, Doc, for your question.
All right, thank you very much. So I guess that would be the last questions for these sessions. So before that, I would like to invite chemist technologist Dr. Nur Hakimin Abdullah, the chairman of RCSSST, to present token of appreciations to Professor ZIAD. Please welcome. Thank you, Dr. Hakimin, and once again, thank you to Professor ZIAD for the great supports to RCSSST 2022. So let us give a big round of applause to Professor ZIAD. All right, so with that, I end the plenary talk sessions of Day 2, RCSSST 2022. So enjoy the conference and have a nice day ahead. So thank you. So I pass it back to Dr. Falik.
Ladies and gentlemen, thank you, Dr. Teo. Here are some of the housekeeping announcements. First, the lunch will be provided at Chirana Restaurant. It will be at the ground floor. So the coupon for lunch for these 2 days are available at the back of your tag. If you don't have it, you can come and see me. The oral presentation will, according to the schedule, is supposed to start at 2, and now it's already 17 minutes, so I presume that we can extend it until 2:15, so we can start at 2:20. So for that, session 1A will be here at the ballroom. Session 1B, Kijang 1, Session 1C, Kijang 2, both at level 1, and Session 1D, Kijang 3 here as well at this level. Ladies and gentlemen, thank you for your time. I'll see you at next session.